I would suggest that we start, because we only have an hour today. So I wanted to say a very warm welcome to everybody. Thank you very much for joining us. Those who don't know me, my name is Rachel Bray, and you can see in my little photo there, I've got my name. I used to be the CERN Alumni Community Manager, and in January, I took over from my colleague Laura Stephanie as Head of Alumni Relations. This is the second virtual company showroom that we're organising. It's an opportunity for companies that have posted job opportunities on the alumni.cern platform to actually come before a live audience and give a presentation about the company, and then also to talk about the opportunities that are available within their companies. So today we're delighted to have Seaborg Technologies. The first 30 minutes of the presentation will be, as I said, about the company and what's available, and then we'll have 30 minutes for Q&A. So please use the chat for your Q&As. I'll also invite you to come on live cam and ask your questions live also, if you'd rather that, so you don't have to listen to me all the time. Let me just admit somebody in the room. There we go. Today we'll be finding out about Seaborg Technologies. They are looking to recruit 50 people, 50 positions in 2021. So come armed with your questions about that. Just a word for everybody, if you're not yet members of alumni.cern, please do join the network. And when you do, please make sure that you keep your profiles up to date. It's very important so that we know what areas of interest you have professionally. And also, you know, we may have occasions also where we might want to invite you to also speak at different events. Here we go. I'm just going to put everybody on mute. There we go. All right, so Seaborg, they started out in 2014 in a Copenhagen cellar. There were 3 physicists who were brewing beer, discussing existential threats, as you do. Now, today, the company employs around 30, no, actually, there's 40 now, I think, nuclear engineers, physicists, chemists, business developers. And they actually own and operate a small-scale laboratory and are well underway to licensing the next generation of nuclear reactors. So today, we're joined by Ask, who is the co-founder and COO of Seaborg Technologies. Ask came to CERN in 2009 and did his PhD in experimental physics at the Atlas Experiment and the Niels Bohr Institute in Copenhagen. Following on from CERN, he moved into a career with machine learning and data science and was an innovation lead for the audience research department at Danish Broadcasting. The last few years, he's been dedicating all of his time to developing sustainable nuclear power in Seaborg, where he's been part of the journey ever since the company started out. Rikke Havre is the head of people and culture. Rikke has more than 15 years of HR experience, and most recently as both a senior human resource business partner and HR solutions manager at Maersk Drilling. She holds a master's degree in business communications. I think that's correct. So without further ado, I will hand the floor over to Ask and Rikke. Thank you very much.
Thank you, Rachel. I'll share my screen because I brought the presentation. So let's just see. There we go. So I'll give a bit of an intro to the company, our journey, and where we are today, as well as on the technology. And I just wanted to say that, as you mentioned, Rachel, with me.
Sorry, you're sharing the presenter view. Maybe you want to share the full screen view.
Yes, let me do that. Thanks. Just a second.
You can swap displays up there.
Yeah.
On top left.
Just need to get back to.
Oh, not.
There we go. Is that better for you?
Yes.
Yes, perfect.
Thank you. So, I wanted to give you a bit of background. As Rachel already mentioned, I started my career as a researcher. I took my PhD at the Niels Bohr Institute, working at the Atlas Experiment. Was part of the multi-lepton group, did trigger work and inner detector work on the TRT. But at the same time, I met up with these guys, and the four of us from the left are actually all physicists with a background from CERN, both experimental particle physics and theoretical high energy physics. As Rachel mentioned, we were concerned about the challenges of the globe. I mean, basically looking at this graph that you've seen in different versions, all of you, the world is really facing an aggravating issue. The amount of reductions we need to do in carbon and greenhouse gas emissions are significant, while both stated and current policies are very far from those goals. We took it even further, and one of our biggest concerns were actually the many parts of the world where energy consumption is going to grow drastically and energy demand is going to grow drastically over the next decades due to both increase in population and to better well-being. All good things, but an area like Southeast Asia, even outside of India and China, more than 240 coal plants are under construction or planned right now. And the reason is that it's a rapidly growing economy with a growing energy demand, a growing population, but also an area where the geographical circumstances mean that it's not easy to build a lot of wind and solar. And there's no hydropower potential. So the potential right now, or the only solution right now, is to build coal power plants. And that means coal power is fast scaling in several of these regions when we look around the world. The company that we founded in that cellar 5 years ago now had the vision to outcompete coal and fossil fuels directly on cost. And it had to be a technology that could be deployed worldwide and could be scaled to meet the solution that we needed. So it needed to be a technology that could be serially produced. Now, the type of reactor that we are developing is called a molten salt reactor. And some of you would probably have heard of it before. I brought a bit of salt. It's not easy to see on the video, so I took a picture as well. But this is a fluorite crystal. The thing about fluorite salts or fluorite crystals is that, well, they melt at typically about 500 degrees Celsius. And then they are liquid until around 1500 degrees where they start to boil. But they actually have no significant vapor pressure in that entire 1000 degrees temperature range. Now, the really interesting part is that a fluorite salt makes strong bonds, chemical bonds to a lot of other chemicals or isotopes, which includes some of the materials, uranium, for instance, that is used for nuclear fuel, but also some of the gases that are produced as fission products. As a rock, it has a very low solubility in water. It's practically insoluble. And the binding of these gases means that you can remove the risk of harmful releases of the gases, which is a game changer in many ways in terms of conventional nuclear power. We built what we call a compact molten salt reactor. I want to start by saying, so in headlines, we can build a reactor where there's no high pressure involved. That means that the risk of meltdown or explosion is in reality taken away. We can bind these gases, even the fission products in the salt, so we can eliminate the risk of harmful releases. And we can design the reactor so that there's no risk of the materials being used for nuclear weapons. It might be even more important to say that a reactor like this can be designed such that it's fueled and you start operating, and then it's a closed cycle for 12 years. After that period, we replace both the reactor core and the fuel inside with a new one that operates for another 24 years, for a total of 24 years of lifetime for such a reactor. It's been done before. A prototype was built in the US already in the 60s. There's been built several around the world since then. One of the challenges at the time was that graphite was used as a so-called moderator. It's a central component, a central material, and it didn't withstand or couldn't withstand the energy density of neutrons when you went to commercial scale reactors. So our take was that a new material was needed, and our edge or our special design is basically based on a different type of moderator. But to be able to deploy this technology worldwide, we also saw a need to go another way than conventional nuclear has for the last decades. So while conventional nuclear has been building bigger and bigger plants to make economy of scale, we wanted to build small reactor modules that could be deployed both more decentrally, but could also be deployed on power barges, boats, ships without an engine. And we've partnered up with the industry in Korea and the Korean shipyards that has for several reasons. One of them is that the current supply chain capacity is to build 300 barges per year. So the scalability is immense. But it also means that we can produce reactors on power barges centrally with very high quality and at very low cost or drastically reduced costs. And having a lead time of 3 years from order to actual grid implementation. Now, a barge like this with 2 reactor cores on it would supply power and heating for 400,000 households. That can be scaled up with modules. I want to talk about a short analogy here, right? So typically, nuclear power plants and even coal power plants have been built at the site. And I mean, when you order a new car for yourself, you take it as the most natural thing that you'll get the finally assembled car. That's what you actually buy. You won't hire 16 engineers who come to your garage and build your new German car. But the reality with, say, nuclear power today is actually that 6,000 people might be flown into that site to assemble and build the final power plant. And that adds a lot of risk of going beyond budgets and delays. If we can turn this around and produce reactor modules that are each of them the size of a standard container and integrate them in a power barge built on Korean shipyards with current infrastructure in place, we can ensure that that's on time and on budget and can be scaled fast. So that's one of our most important business strategy plans for marketing. The other main barrier for nuclear power today has been the regulatory approval. And we were happy to announce this fall that we were the first reactor development company in the world who got the first approval in what is called the American Bureau of Shipping's new technology qualification. So this is a regulatory pathway for maritime technologies that we are following to basically approve that the reactor is safe. The framework allows us to get the first reactor online in 2025 and obtain type approval in 2026 if we meet all our deadlines. And that by itself would be a significant milestone. To make that happen, we need a lot of gifted people. We are much more than the 5 physicists in a basement that we started out as. As Rachel mentioned, we are actually close to 40 today already, and we are hiring at least 40 more in 2021. We have partnerships around the world. Denmark is a small country. We want to develop the reactor here, but we need partners from all around the world for both downstream and upstream supply chain. We want to develop the technology in Denmark with the bright hats that we have already accumulated here, but we want to build the power plant in Korea, and then we want to deliver power globally. While the first market will likely be Southeast Asia, there's no reason that this won't be shipped to other parts of the world. And we think it's an absolute necessity for new generations of nuclear that they are more modular and that they can actually be deployed globally if they are to make an impact and become a part of the technology of the future. I want to give you this one example. If we are to, not just Seaborg, but everybody, if Seaborg was to replace all coal power, fossil power in Southeast Asia, outside India and China, just with the already estimated growth, we would need 7,500 reactors, power barges, by 2040. Now, the supply chain that is in Korea could actually build this if we could build the reactor modules. So this tells you a bit about the challenge, but also about the potential for scaling. Now, I actually want to finish quite early here, so we have a lot of questions both for the technology and for some of the profiles that we'll be looking to hire. before going into that, I want to say so as a company, we are extending our laboratory capacity. So we're actually going to be building an isotope laboratory in Denmark, and we're already expanding the current lab. We're also going to be building a workshop, a bigger workshop than we already have. And then, of course, a lot of the work is going to be carried out also in South Korea and other countries. And there's no question that if we are to meet the ambitious plan that we have, we need talented thinkers, and we need people who have both experience from academia, and we also need people who have experience from the industry. And I actually think I'd like to give the word to you, Rikke, and then we can go back and take questions on everything afterwards. I'll be happy to talk also about the tech. Yeah, over to you.
All right. So yes, of course, as Ask is saying, we're facing challenges. One of the big ones is to find people who can build this technology. And it's sort of a niche, of course, because especially here in Denmark, very difficult to find people with this experience. Nuclear is not really the thing that people have of experience here in Denmark, because it's not on the map yet.
No.
So that means that we have to look for talent all over the world. And it's also a niche in the way that it's not like going out finding a finance manager or something like that. And what we're looking for right now, especially engineers, and here in the presentation, you can see some of the titles that we're looking for. And the engineering department is definitely the biggest department we're trying to build. Of course, it's also people who have to work together with the chemists and the physicists, which means that it's also someone who potentially or comes with industrial experience, who's been working, collaborating in teams, project management. But still, we're also looking for people who have the academic background. So it's sort of a mix in between these two worlds that we're looking for. Yeah, and of course also then we have to build up the whole support system of functions. So that's why I joined as HR, or people and culture. And we're also looking for procurement and finance specialists. Yeah. Should we mention?
Yeah, I can. Yeah, first of all, I can add that I'm going to be posting the jobs on the CERN Alumni network, and we also have them on our website. So there will be a lot more information coming up there. I also wanted to mention, I mean, the journey I took myself from academia to first private industry and then to a startup, and now I'm not sure we can even say we are a startup anymore. We're at least also a fast-growing company. I mean, there's a lot of learnings that we've made, and we part of our success so far has been that we have had a sound academic foundation. I mean, we've hired technical people to begin with, and had a vision to be technically leading. So you might even say that we underprioritized a lot of the other parts of the organization until recently. But that also means that we have a team of really gifted technical people, and it's meant that we've been able to drive it this far. And we're looking to hire people with all kind of backgrounds to support both journeys, as Rikke says as well. Rachel, I'd like to take it over to you so we can start with some of the questions.
Great. Yes, thank you to both of you for a fantastic presentation. It's super interesting. I wondered if we could throw it out there. Does anybody have any questions that they would want to ask or Rikke, either about the technologies or about the types of profiles they're looking for? Any tips, perhaps, that can be given for people who are thinking of applying? Don't be shy. Otherwise, I can start it off, maybe with a naive question. No, sorry, did someone have a question here?
I have a question. This is
great.
Ben.
Please go ahead, Ben.
I'm still speaking to the presentation screen. So
there we go.
Right. Okay. Before I came to CERN many moons ago, I was a reactor engineer myself, and I worked in fast breeder reactors. So just let me say a couple of things before my question. I do agree with the concept of the molten salt reactor. There have been, as you said, there have been many. It's very, very promising. But in your particular case, I haven't seen any technical details. And the most I found was on your Wikipedia page, but even there, the link to your white paper from 2015 is broken. It's a 404 error at the moment. Which
that's also quite old, so I'm happy that link was broken.
Right. So my question is, where is your technical information, and what is the state of your collaboration with other projects, if any? Because there are many other projects like this going on along. Okay, that's my question.
Okay, so thanks. So it's a thermal reactor we are building. It's moderated, and I think there's a lot of really interesting development ongoing. You could call it our competitors. You could also call it collaborators. We hope that several technologies will come to market, because that's going to make it easier for all of us. We are developing a fluorite-based molten salt reactor, and it's the moderator is a hydroxide salt. So that's we have a patented system for the hydroxide moderator. So that's one of the new things we brought to the table. The development we focus on is on the actual reactor module, the primary system and the secondary heat transfer system, while everything from generator, boiler, all of the steam cycle and outside, even control room, is being developed in collaboration with partners in Korea. Now, I can't disclose everything right now, unfortunately, but that's just as it is. But I can say it's Korean partners, a lot of that.
Okay, but just one little. The only fact that I was able to find is that you've got your moderator in separate pipes from your nuclear fuel.
Yes, correct.
And I just found one mention of that, and that's all. Okay, is that patented or something?
Yes. So I think, yes. I want to add that there's been a lot of buzz around thorium reactors. And the white paper you mentioned, I mean, where we started, we actually thought we should build a molten salt thorium reactor. Yeah. Now, thorium has some advantages, both in abundance and in the fuel cycle that you can run as a reactor. But we chose, at least for the first generation of reactors, we are completely open now about that we will use a uranium fuel cycle to begin with. Now, it's in many ways, it's similar to a conventional reactor, with the exception that molten salt, I mean, the state that you have your spent fuel on makes reprocessing much easier in terms of all the non-proliferation rules. I'm sure you know that it has to be done at a central facility, but it is actually a lot easier to recycle a lot of the long life fuel. I mean, the fission products are still going to be there. We're going to decommission them just like you do in the conventional supply chain, or in, say, for hospitals or at CERN. But the long-lived waste, we plan to recycle a big part of that, but in next generation of reactors. So we're going to start with a uranium fuel cycle. The size of the reactor, it's a 250 megawatt thermal reactor. That's around 100 megawatt electric per reactor module. And it is the size of a standard container, more or less. I mean, that's including the heat exchanger for the primary module. So the core itself is 2 by 2 meters as a cylinder. And the reason we wanted to build it as compact as it is there was actually that we saw a need for a more, both the modular serial production, and there's simply smaller risks if you can build it smaller. And because it allowed us to make more decentral deployment. I mean, having a power barge with the 200 megawatt electric power is something that you can plug into current power grids in many harbors, even in Southeast Asia. So the power plant, I didn't specify here, but the power barge will be sailed into a shielded harbor, and you will set up fences around it, right? But it's a much smaller site compared to what you know of as a conventional nuclear power plant site.
Thanks a lot.
Thank you. We have Michele, who's raised his hand, his virtual hand. I hand over to you, Michele.
Yeah, thank you. Thank you, the speaker, for his presentation. I'm sharing the same remarks made by the previous intervention. But on top of that, I would like to understand who are the shareholders of this company, because the product is still in the R&D stage, and you need a large amount of money to reach the product which can be sold on the market. Thank you.
So thanks. I think that's a really good question. So when we started off, I mean, we came from academia, but we also, we had a vision that if this technology should reach market within, say, a foreseeable timeline, it needed to be commercially or privately driven. Part of the reasoning was that while sharing information is really, really good in many aspects, in academia, it can be a hindrance to some of these technologies to actually get it to market. While the other thing was that academic collaboration brings little in terms of groundbreaking, but when you want to get the product to market, it can also be a hindrance. And the majority of our financing is from private investors. It's both from what you might call visionary angel investors, in sustainability, and it's also some funds, both Danish national funds and international funds that have invested in the company. We have also received grants from both the Danish state and from Europe, but the majority of our funding is private. And we think it had to be that way to actually pursue the timeline that we want to pursue. We want to set this up as industry partnerships and with the potential of the technology driving the investments. And even though we succeeded with a major funding round this autumn, we are of course going to need other funding rounds, at least one more funding round before we get the product to market. Yeah.
Thank you.
As all of you who have worked in prototyping, even though, I mean, a molten salt reactor is a complex thing, but the size of the course that we are developing helps us in the sense that the smaller your prototype is, the easier it is actually to build. And that also means that our first prototype will also be the first commercial reactor. We will get the approval directly on that. And that cuts away several years, of course, of trial and error. We will have to build that core several times before it's turned into a reactor. That's another story, but it will be the commercial reactor.
Thank you. We have a question, if we can, in the chat from Adrian. I don't know if I've pronounced your name correctly. I apologize if I haven't. Would you like to come on camera and ask your question? Then we'll go to Chiara and then to Rasmus.
Yeah, sure.
Thank you.
Hi. Yeah, thanks. Yeah, I would like to know if you only foresee the reactors to be in the harbor or also on land.
Yeah, so when we started developing this technology, I mean, we hadn't considered a maritime approach at all. So we were developing towards a land-based reactor. I mean, like everything before. The reason that we decided to take the maritime approach is, as I mentioned, twofold. So one of them is being able to use these shipyards that are some of the most effective and highest quality factories in the world for serial production of power barges and allowing us to have central production. And especially in a country like Korea, where there's also significant competences within the nuclear regulatory framework and skill sets needed. But the other part was actually the regulatory approach. So ABS is a consultancy bureau. It's a society. It's called Maritime Society. They follow UN guidelines. They'll have to. They even follow IMO's laws, and we will still follow IAEA's guidelines, the International Atomic Energy Agency. We'll need to, of course. but the difference is that while a new technology has so far been reliant on a national government creating the first set of safety checks and defining their own laws, we can use a bureau with a lot of manpower, much better skill sets than one national state to start off with an international class approval. And that we see as a significant change to how it's been done before. Now, if we want to go to land-based reactors with time, I think we will. But we actually see so large a potential an advantage in the maritime approach that we're not going to do it in the near future. It's not going to be within the first decade.
Okay, all right. Thank you.
Okay, let's move to Chiara, who has a question which is more related, moving away from the technology side of things, more related to hiring, the hiring process. So Chiara, would you like to ask your question, please?
Yeah, can you hear me? Yes, I think so. Yeah, of course, all the technological part is super interesting, and I would like to know much more about it, but I also wanted to ask a bit more practically speaking concerning the hiring, so geographically where this hiring would be placed, because I guess if it is an international collaboration, it's probably not all like in Denmark or Korea, but it will be probably spread. And maybe if you can then give a little bit more information, even if you said that it will come later in a different platform, but if you can say a bit more about the profiles you see for physicists that work in LHC experiments, and possibly, with also some experience afterwards, but what do you see? I saw some positions about analysts, etc. If you can say a little bit more about the different positions you offer.
Yeah, so first of all, your first question, the hiring is in Denmark. So we're based in Copenhagen in Denmark, and that's where our headquarters is and where we employ basically everyone. We have a couple of people sitting in Korea, but until the building process, then everything's here. And for the positions that we have within our analysis team, as you said already, you've seen it on the job portal. We have a multi-physicist, analyst and safety analyst. We have a stress analyst we're looking for. All the technical aspects of the profiles, probably more for us to respond to. So, but as I mentioned before, we really would like some sort of mix between having employees with the academic background, thorough academic background, but also some that come with some industrial experience.
Yeah, I can add that. So we are already people from 5 continents here in the headquarters in Copenhagen. So it is a bit like being back at CERN. But and you asked some of the skills. I mean, it's going to be a variety in the analysis group, as we call it. But of course, people who have experience in either, say, neutron transportation code or neutron modeling, or what we call multiphysics, coupling irradiation modeling with thermal hydraulics, and other types of the thermal hydraulics modeling is definitely interesting. But there's a variety of skills. I mean, we in simulation and modeling of the reactor core, the processes going on there, the heat transportation and that, and also specific to materials like the stress analyst with both mechanical properties and all the things you need there. Yeah.
Thanks.
Okay, thank you. So now we have Rasmus who has a question. We'll then pass on to Julia and then back to Michele. So please, Rasmus, go ahead.
Yeah, hi guys. So I actually have 2 questions. One is technical. So you talked briefly about the thorium reactor. So I would be interested in if you could maybe elaborate a bit more on why you didn't choose to go with that direction, because it seems quite popular and kind of a buzzword these days to use thorium. And the second question is most HR question. If you have any positions for more electrical engineers, such as myself.
So I'll start off. So there's several reasons, but I think one of the main reasons for not going with thorium is that the fuel supply chain is not set up, and we think it would be a huge challenge to get a fuel supply chain set up within the time frame that we are looking to deploy this reactor at. So that said, we actually look into deploying a thorium molten salt reactor in a later generation, because there are some advantages to it, but it's not something that we work on currently. The other aspect is that while thorium has a lot of advantages, it also brings some challenges both to the chemistry and to the non-proliferation issues. Because in a thorium molten salt reactor, you would typically, if you want all the benefits, you would have to continuously add more fuel and take out fuel. So you actually have an opening into your reactor core at the site. While we can develop a product right now that is entirely sealed for those 12 years in terms of taking radioactive material out. And that's a huge difference. It makes it much easier, not only to guarantee safety, but also to live up to the rules that we need to comply with. So that's a short answer. And your second question was in terms of whether we also knew people to set up the electrical systems.
Yeah, and as I said, the engineering department is the biggest team we're building up. And it's basically the two different systems, salt and gas. And we need a lot of mechanical engineers. But I know that we're also looking for competences within electrical engineering. So it's not, we don't have a specific electrical engineer position on the job portal right now. But we have a design engineer, which is someone who could come with different backgrounds. So if you have an interest, it's just going to the job portal and applying.
Okay. Yeah, okay, thanks.
Keep your eyes peeled on alumni.cern because we'll be publishing the opportunities there. Great. So now we have a question from Julia, then we'll go to Michele and then to Samid. So Julia, fire away if you'd like to ask your question on camera.
Yeah, hi, thanks a lot. So this is more of a curiosity because you were mentioning that this technology is not totally new, if I got this right. So it was already like prototype in the US years ago. So I was just curious about the reasons why then it didn't spread at the time.
Yes, that's the first question we asked ourselves, actually. We starting on this. So we were just, I mean, this started out as an academic curiosity, right? We were modeling old reactor designs for ourselves and just looking into them. And we asked ourselves, why wasn't this taken further? And well, there was more research done, but in the US, it was basically closed down after the 60s or started beginning of 70s. China had a prototype in the 70s, and there's been a bit of development around the world with thermal reactors. But the short story is that I think there's two very clear reasons. One was that, I mean, the molten salt reactor experiment in the US had a graphite moderator. It was a couple of megawatts in power density in the core. Now, for a commercial reactor, you will need 10 times that. And graphite simply doesn't withstand the neutron flux when you go to 10 times higher flux. So it starts to crack and break up, and it lasts somewhere between 3 months and a couple of years in best case scenarios. Some of our competitors or other developers have been looking into making graphite better. And it might be possible to extend that lifetime. We just didn't see that as an opportunity. But I think that was one of the reasons that was actually closed down at the time. The other thing was that this is remember, this is a liquid, right? Where you have the radioisotopes inside. So opposed to a conventional reactor where you have solid rocks and you can do static calculations of the fission products and the fission process. Here you have something that's moving. So it's dynamics and the modeling requires supercomputers. So the other part of the story is that it's only 10 years ago that we started having the computational capacity available to people like us to actually model this and say, how's our reactor going to perform? And I mean, getting a reactor approved today without having a model that actually explains what's going to happen is impossible. And that's a major difference from, I mean, in the 60s, they just built it and looked at what happened. I think that's one of the biggest reasons that we've seen this renewed interest. It's not only us, it's also TerraPower, backed by Bill Gates, building a fast chloride reactor. It's Moltex in the UK building a stable salt reactor. And there's several developers looking into the molten salt concept in various forms. And they've emerged within the last decade, all of them private.
Thanks. Yeah, thanks a lot.
Okay, so we'll move to Michele, who has his hand up, then Samid, Johannes, and we also have a question from Andre.
Thank you, Raquel. I suppose that the company has developed a business plan. Can they elaborate on that?
Mikhail, could you repeat that question?
I suppose that you have make a business plan. Could you elaborate on that?
Yes. I mean, the business plan is actually tied up very closely both to the regulatory process and to the first customers. And I mean, so it might be, I might not be able to elaborate too much about customers, but it is important for us to be a reactor developer as a company, as I already mentioned, and have partners building the power batch around it, and being part of the regulatory process as well. Now, the business model, I mean, it's the power batch by itself. The current estimates shows us that we can actually make that compete with or even outcompete coal on price without subsidies. And the reasons that we can cut down costs is there's several reasons. It helps having something serially produced, but I think it's even more important that because we have no high pressure, I mean, we have a couple of bars pressure in the reactor, opposed to a conventional reactor where you have 150 bars or even more. We don't need the big and very costly pressure barriers that you need, and that's a significant cost driver. There's other systems that we simply don't need without compromising safety or security. So that can actually cost or drive costs down. Now, one of the uncertainties in terms of cost is, of course, the materials lifetime. Can we actually ensure that the materials with the corrosion last for more than 12 years? Now, without disclosing anything, I can say that has been the topic of study for many of the reactor developers, whether how long can they make their materials last? Is it feasible to have 12 years or even 20 years of lifetime, or is it shorter? Some of our competitors work towards a much shorter reactor core lifetime. Thorium from the US has a 4-year reactor core lifetime as their development targets. So there's different approaches to getting to market. Yes. That answered, I hope, at least part of your question. Yeah, and I also want to say, so we want to produce power. I mean, it's got to be a batch with a steam turbine producing electricity. It can produce district heating as well, if that's possible at the site, because it's at the same temperature. The steam cycle is basically like you know it from biomass plants or coal power plants. It's a completely normal, standard thermal cycle there. We just get the energy from
listen, just CERN buys actually electricity from France, EDF, and the cost is 27 Swiss francs per megawatt. You will be able to be competitor.
I mean, that's a target. I think, I mean, France also has some good infrastructure on electricity, right? There's both the stability, which is an important aspect, and there's the price. Being able to deliver a stable supply and at a good price. So the primary markets, let's just say we want to go to Indonesia and power Indonesia. One of the challenges there is actually that there's a huge variability. So while part of the electricity comes from coal, some comes from gas, a lot of that coal has to be sailed in, and the infrastructure is not well developed in terms of grids and so forth. So there's a lot of cost associated with actually producing electricity and especially expanding that grid. So having something that's, of course, not just plug and play, but still something that can be sailed to a harbor and then a site set up around that, but at a capacity that can be installed in the grid is a huge advantage, and means that compared to every competing technology there, we will be far cheaper. But the goal is to directly compete with coal.
Thank you. Good luck.
Okay, so thank you very much. We now move on to Samid, who wanted to ask his question on camera, and then we have Johannes and Andre. So Samid, take it away, please.
Thanks, Ask, for the very nice presentation. So I understand that you have partners in South Korea, and that's probably where you will start. Do you already have you already investigated expansion to other countries, so in Southeast Asia, or what's your, let's say, long-term plan?
Yeah, so there's different answers to that question, all of them right. So shipyards, we want to build this on shipyards going forward, and it has to be in countries where the shipyards have a very high quality. I mean, we don't want it cheap. We want high quality. It's also a lot less costly than many other ways of producing it, but quality is essential. Japan also has shipyards with very high standards. Singapore has shipyards with high standards. There are several opportunities. There's also opportunities in Europe. So of course we will. That's a continuous assessment. What's the right thing to do? There are several options. I think the current capacity in Korea alone is around 300 power barges per year. So it takes a bit of time before we have a bottlenecking capacity there. That would be 600 reactors for us to build.
So maybe just a very quick follow-up. What would you say about Malaysia or Indonesia, because they might not be at the same level, but close? Just curious.
I think they are excellent examples of countries that will go through a huge, increase in energy consumption, both population growth and wealth. People get richer. They get electricity in the houses. They get more schools. They get more clean water. It's basic needs that are filled with the energy growth as well, right? It's not just industry. And they'll need a technology to replace part of the coal that will otherwise be built, because it's not feasible to do that with wind alone, for instance, in Malaysia. So Malaysia is a very good example of a candidate market, yes. And we are in dialogue with the potential customers there for sure.
Awesome, thanks.
Okay, so we have Johannes, who's had his hand up for the past 5 minutes or so. So let's hand over to you, Johannes. Thank you.
Thank you. Well, my question is in two parts. So the first thing is, how do you see the kind of profiles you're looking for developing in the next couple of years? So right now you're mostly looking for engineers, as I can see, but how will that develop? And then my second question is, what kind of experiments or tests are you looking to do at the moment with your new labs you're setting up?
All right, the first part, at some point for sure, we're going to need some more business development, commercial team, and with that also the other support functions. But the important part is, of course, to have a product to sell. So that's why it's mostly focused on the technical skills right now.
Yes. Yeah, and I can add, so we are expanding the lab right now. We've been doing corrosion studies as some of the most important experiments there, both in hydroxides and fluorite salts. You do this redox control, various ways of actually ensuring that you extend the lifetime of the materials around that salt. Irradiation tests of materials is another aspect that we have started, but there we will look a lot to collaboration. We will be sending someone to Karlsruhe right now. We also have dialogues and collaboration with the national labs in the US, and that will definitely become more with time. We also have collaboration, a bit of collaboration with the European spallation source, actually. In terms of product building, we need to go through the same journey that CERN has done many times, right, with some of the experiments there. And in the initial prototyping, there's a lot of workshop work where you build a product, you realize that we designed it wrong. When you start assembling it, part of it need to be iterated. So just to give you the general phases that we're in now, the approval that we got was based on what you call the basic design phase. And we are in what you call the detailed designing in engineering terms right now. And when we get the third phase of the approval, that will be when we are allowed to build the prototype that can be commercialized. And there's two phases following that where we get operational and class approval, but after the initial reactor has been approved. And with that, there will be iterations in design and learnings. And we're not at a stage now where we know where every bolt in the reactor needs to be, because part of that we know is going to change when we perform experiments and learn more.
Thank you. So now, Andre, would you like to come on camera and ask your question, please?
Okay, thank you. Thank you, Ask, and thank you for this presentation. I'd like to have one more question about fuel cycle. So I understood totally the reasons about choosing uranium, which makes total sense for me. Could you please elaborate on what is the current status of fuel supply agreements you have, and on reprocessing decommissioning status? The reason for this is not just purely, let's say, technical curiosity, but also business, because from my understanding, several companies may not sign supply agreement before you have license for operating the reactor, which is due in 2025, as far as I believe. So how do you accommodate this possible delay? And second backup is about geography. Do you want to supply, fuel, and decommission everything also in Asian region or somewhere in Europe or elsewhere? Thank you.
Yes, so really relevant and good questions, Andre. To start with supply of fuel, Seaborg doesn't look to develop the fuel ourselves, obviously, right? We'll need partners with that. We'll use the existing supply chain. Now, what we need is a fluorite salt with uranium in it. But the good thing is that uranium fluoride is actually part of the supply chain already. I mean, it's one of the processing steps where you produce both hectafluorite and some of the other types. That said, it's not commercially available yet. We couldn't order our salt right now. We have been in dialogue. I want to be honest that fuel supply is one of the risks that could delay start of the first reactor for two reasons. Both when we actually can have it commercially available through our partners, even though they've done a lot of development, is still, I mean, that could be delayed. The other part is actually uranium enrichment supply. A very large fraction of the world's uranium comes from, enriched uranium comes from Russia right now. And the demand hasn't been growing for some time. And that also means that capacity is at a steady state. So being able to scale, it would be a concern to begin with. It's known technology, so it's something that can be done, but how fast it can be done is uncertain. That's typically a concern after the first reactor or first power batch only. In terms of decommissioning, we also want to use existing supply chain. And while fluorite salts are in a different state than what is being used today, it's something that's been researched a lot. France had a program even on decommissioning where they wanted to look into changing from metal states to fluorite states because of the benefits and the barrier that the fluorite salt has. We hope that we will be able to recycle. So we actually hope that we will get approval to take it back to a central facility and do reprocessing. But the approval for the first reactor will not contain that because we won't be able to get it within that time. So that's something we'll apply for as the reactor is on market. We'll try to set up everything needed to be able to take it back for central reprocessing. And where that reprocessing facility is not settled yet. But it must be in a central country where there's nuclear authorities already that are well trusted in the world. There's only a couple around the world right now that would actually have the technology capacity.
Thank you for the details.
Okay, so we have about approximately 7 minutes left. So now is the time to be asking your questions. I don't know if anybody wants to raise their hand or if they're perhaps shy, put their questions into the chat. Whilst we're waiting for that, I was wondering in terms of something, Rikke, that you said about, you'd like to have a mixture of people with industrial experience and also with an academic background. What's the best way, you think, for somebody who works at CERN to actually demonstrate that they have this type of sort of more industrial experience if they've been working at CERN? Or maybe ask either is for either of you two.
I don't think I have the answer to that, but I know that it's something we've been discussing. Because when you do a lot of research, it's difficult to also have that at least industrial experience from the corporate world. So that's also why we want to get closer to a definition of what is it we're looking for. So that discussion is something we already took up. But I don't know if you have anything to add on the...
No, I think, I can, my only experience was that I took a leap when I went from academia to the private industry, first in IT consulting and then in other parts of the industry. And there was a lot of things that I actually knew how to do from my research career, but I didn't use the same words when I was for what people called it, right? that's part of it, right? And another is how to approach projects and when to actually go out and build something or test out stuff without with the risk of breaking it, for instance. So one of the things that's both interesting and difficult in Seaborg is that sometimes we actually want to drive, when it's not with the radioactive materials at least, we want to drive some of our experiments forward faster with the risk of breaking stuff. And that can be a really good way to get a long way fast. But it also, it can be very intimidating, especially if you come from a scientific career where you cannot break stuff basically during the time. That's just one example, right? But it's been one of our learnings that it gives us a lot to have people from different backgrounds. That's been very, very healthy for us. And we want to continue that going forward.
Just to follow up on that one, can you give any practical tips to anybody, you know, in terms, you said, you know, the business jargon and stuff like that? I know that Rasmus is coming up with a question after me, but if you have any quick tips, perhaps, on how people can develop that side, you know, thinking that they might be applying for a job in industry, or, you know, what can they do? How can they translate what they've been doing in academia to something which is sort of more understandable in the business world?
I think a lot of it also comes down to the personality of people. Understanding, being able to see things from different perspectives. When you've been, let's say, doing a PhD, it's a lot about focusing on within your area, but have the ability to also think other perspectives. That's a good quality to have. And we also talked a bit about this meeting deadlines. When you work in the industrial part of it, you have customers, you have investors, shareholders, and so on. They want to see results. So deadlines are
we seem to have lost, we lost you for a moment. It got stuck for a moment. Thank you. I know that because we don't have much time, I was wondering if Rasmus would like to jump in with this question.
Yeah, it's just a quick one. You touched briefly, asked upon the whole simulation stuff, and also the question from Johannes is like, what about programmers and stuff like that for simulation, or maybe user interfaces for controlling the whole thing? I think a lot of programmers at CERN.
Yeah, so we basically started, the white paper that was mentioned was made literally in a basement. We had access to some supercomputers, but what we started off as and being good at was neutronics modeling and thermal hydraulics modeling, and combining those two, and started doing burn-up studies and some of these things where it's a lot of programming and modeling of reactors. And we've transited from them, but we still need a lot of code, still even code development and simulations and modeling to comply and show that our experiments are actually correct, or the other way around, get validation from experiments. We tend to hire people who are specialized in the type of programming modeling that we need, and then hope that they're also qualified coders. And what I learned at CERN was that a lot of physicists are actually very good at coding, even though they might not know the jargon or lingo again from an IT consultancy. They actually are both very structured and good in the way that they do things. So we had good experience hiring people with that background before.
And I think we've got one, if you've if still okay with you, we've got one last question from Sami before we wrap up and we find out more about where people can find out about the jobs, etc. So Sami, take it away, please.
Yeah, maybe this is also following on from the recent questions. You had a background in experimental physics, and a lot of experimental physicists at CERN are on paper physicists, but in reality, project managers, where they do everything from the design phase and then procurement and then putting things together and then commissioning and testing. So is that kind of the profile that you're looking for in your field right now, or is it more of specialized programmers, specialized analysts? Is that what you're implying?
We're looking for a mix of both. So definitely that would also be relevant. And I actually suggest, because if you cannot find a job ad that matches exactly your skills, don't use the unsolicited one, because we get a lot of applications into that one. I think it's better to connect with either Ask or me on LinkedIn, and then we get your CV through there.
Yeah.
Great. So I think now we've come to 1 o'clock, so the hour went really, really fast. So I'd like to say a huge thank you to Ask Enrique for having joined us today and having told us more about the technology and also the types of opportunities that are available. Thanks to everybody else who followed. We will be publishing the recording of the event, and Ask, perhaps you'd be kind enough to share the slides with us as well, so that we can share them. There's been a lot of interest, as I said, in your company. So if people want to find out more, indeed, you can contact Enrique on LinkedIn, but I would also encourage people to contact Ask on alumni.cern. Don't forget, we've got the job opportunities that will be appearing there soon. Ask Enrique, I leave you with the last words. Put you on the spot. You've got a pitch, a 30-second pitch.
No, I think it's always fun being back at CERN, and I think even at a virtual showroom, it kind of feels like some of the vibe is still here. So thanks for that, and thanks for the opportunity. Yeah.
Thank you. It's been great. Thank you so much, and thanks to everybody for joining. And I wish everyone a bon appetit if in your time zone it is indeed lunchtime. Thank you very much, and let's stay connected. Thank you. Bye-bye.